So I want us to continue with electrochemistry. Having looked at Faraday's laws in our previous engagements, we shall still look at more of calculations on electrolysis. Each example I deal with here has something unique with it. That's why I want to give some good time to these calculations. And we are having example 5, which says an electric current was passed through a solution of copper 2 sulfate. An electric current was passed through a solution of copper 2 sulfate that was electrolyzed between platinum electrodes for 1 hour. So since the electrodes used in this case are inert, then there is no factor that we talked about, the other factor of effect of an electrode. We said copper 2 sulfate is one of the electrolytes affected if copper electrodes are used. Now, if you pass an electric current through a solution of copper 2 sulfate for 1 hour, you're being asked one, to calculate the strength of the electric current used to deposit (0.16 grams) of copper. 2, you also asked to calculate. Somebody is saying if the cell above, the electrolytic cell above, was in a series with a silver nitrate cell, if it is in a series with a silver nitrate cell, that implies that the same current that passes through this cell, I think you know what the word in a series means from your physics. The current that passes through the first cell is the same current that will pass through the silver nitrate cell. That's the trick there. Somebody is telling you to calculate the mass of silver deposited. Where is the silver deposited? Silver ions are cations, so they will migrate to the cathode and get deposited there as silver metal. Calculate the mass of silver deposited at the cathode. So this is what we have. Somebody is asking us to calculate the strength of the electric current. Current is I, and we should always get it in amperes. So how do we get the current in amperes? If you remember the expressions for these calculations, we usually said that charge is equal to current times time. This implies that to get the current they want us to get, we shall get the charge over the time. We have the time as 1 hour. But I remember telling you that when we are dealing with the time in electrochemistry, we convert it to seconds. and 1 hour is 60 minutes. The 60 minutes each is 60 seconds. So 1 hour will be 60 by 60, which is 3,600 seconds. But we don't have the charge. According to this expression, we don't have the charge. So how do we get the charge? So the trick is that get the charge first, substitute it in this expression and get the current. And how shall we get the charge? To get the charge, now that takes us to Faraday's second law of electrolysis, if you remember it. Faraday's second law of electrolysis stated that the quantity of electricity required to liberate 1 mole of an element is proportional to the charge number of its ion. So, if we are looking at, excuse me, if you are looking at copper being deposited, that copper is being deposited as a metal on the cathode, where the copper ions migrate. That implies that we shall need the equation at the cathode. The equation at the cathode is simply copper 2 ions migrating there to deposit copper that they are talking about. This is balanced by adding 2 electrons here. Now, if copper is deposited there, this expression is going to help us get the charge. Okay, we shall say that 1 mole of copper is deposited by 2 moles of electrons. We want to get the charge now. 1 mole of copper means the mass of copper. The mass of copper is it 63.4? Yes, that is according to the A-level periodic table. RFM of copper is 63.4. That is being deposited by 2 Faradays. And when you talk of 2 Faradays, that will be 2 times, because of these 2, 96500 coulombs of charge. Are we together? Now you ask yourself, how about this mass here that the question is talking about, 0.16 grams? So 0.16 grams of copper is deposited by 0.16 times 2 times 96500 over 63.4 coulombs. And this one, when you press your calculator very well, it gives you 322.68 coulombs of charge. That's what it gives you. That's the quantity of charge that will deposit the given mass of copper. Now that implies that we can now proceed with our calculation and complete it. I wrote this at first to show you the approach, but this is what should actually be done first. However, if you do this and then come back here and do the substitution, no problem. So your I will be 322.68 out of the time. The time is 1 hour. Each hour has 60 minutes. Each minute has 60 seconds. That's how you convert the time to seconds. If it's in hours, multiply by 60, again by 60. When you do this very well, you get your current as 0.0896 amperes. That will be your current. And that makes our part A quite well done. makes our part a quite well done and gives you your good marks. If they are 4 or 3.5, something like that. Now, the second part of the question is telling us to do what? It's telling us to calculate if the electric cell is in series with the silver nitrate cell, calculate the mass of silver deposited at the cathode. So if you look at that, that is part B now. I've told you that statement means that the same current that passes through the first cell is the same current that passes through that cell, which is 0.08 96. Is it 896? Yes, amperes. What else do you need to know? The time is the same. The time is still 1 hour. So that means we can get the charge now. Actually, the charge is also the same as in the first cell, 322.68 coulombs. They're now asking us the mass of silver deposited at the cathode. So what is the equation for this reaction now? The equation is simply silver ions plus an electron is giving us metallic silver at the cathode. That is the equation at cathode. What does this imply? According to Faraday's second law, that 1 mole of silver, in other words, to make your work very simple, because you're getting mass, you should begin with the charge. Okay, 1 mole of electrons, because of this, deposits 1 mole of silver. And this implies that 1 times 96500 coulombs deposit silver in terms of mass. 1 mole of silver is 108. So that would be 108 grams of silver. How about this charge now? It is 22.68 coulombs deposit. These are like ratios and proportions, and then some molar concept incorporated. So this will be 322.68 times 108 out of 96500 grams. And when you do this calculation perfectly, you get 0.361 grams of silver. I hope that's also well understood. If it is well understood, then allow me to proceed to another example. In my other example, I have this question. The question says, a current of 0.89.6 milliamperes, MA means milliamperes, microamperes, sorry, was passed through an electrolytic cell containing sulfuric acid electrolyzed between platinum electrodes. And this took us 1 hour. Somebody is asking you to calculate volume of gas. Calculate the volume of gas measured at STP, liberated. That's the question. That is the question. Now here, actually, let me change this question directly. Actually, the volume of gas measured at 15 degrees Celsius and 1,000 kilopascals that was liberated. Now this question will require us to first of all know the theory here. Okay, let us know what we are. The theory suggests that during electrolysis of sulfuric acid dilute, we have hydrogen ions, both from water and sulfuric acid. Then we have sulfate ions from sulfuric acid and hydroxide ions from water. Water will give us still hydrogen ions. This means that at the cathode, where the positively charged ions migrate, the hydrogen ions there are going to liberate hydrogen gas. That's why the question is talking about gases. So 2 balance, 2 electrons. Then at the anode, these 2 migrate. And at the anode, since the hydroxide ions are lower in the electrochemical series, then we shall have it giving us oxygen gas and water. Remember that equation. To balance it, we have to put a 2 here. That makes our oxygens 4, then a 4 here. The hydrogens are balancing already. What's not balancing is the charge. Then we add the 4 electrons on the product side. I hope you remember that very well. Now, we are having gases. We're having this gas here at the anode. We're having this gas here at the cathode. And the question is asking us the volume of gas measured at STP liberated. That implies that we should add the volume of oxygen liberated at the anode also plus the volume of hydrogen liberated at the cathode to get the total volume of the gas required. But before we do that, we need to see what are we given and which charge should we use. That's the purpose of this current and this time. Okay, so we know from Faraday's second law, first law, that Q is equal to IT, and Q is equal to our current here is 89.6 microamperes. That word micro should be removed from the current, and it means that you multiply the current by 10 power negative 3. That's what it means. It is milliampere, that's not micro. Micro is usually this symbol here. But that one is implication that you multiply that current by 10 power negative 3 to convert it to amperes. Then our time is 1 times 60 times 60. When you do that calculation, you get your current as 322.56 coulombs of charge. Now that is the charge that was really passed through the electric current. And we need to see that that charge is going to liberate a certain volume of oxygen, oxygen at the anode, and a certain volume of hydrogen, hydrogen at the cathode. So what shall we say? We shall say that at cathode, what do we have there? At the cathode, we have hydrogen ions plus 2 electrons giving us hydrogen gas. So we see it that we see it that 2 moles of electrons. I'm beginning with the electrons are not 1 mole of hydrogen because we are having the charge. So 2 moles of electrons liberate 1 mole. This is 1 mole of hydrogen gas. And that implies that 2 times 96500 coulombs liberated 1 mole of hydrogen. How about now, if the question was at STP, if this was STP and these are not the conditions that we are given, then we would simply write here 1 times 22.4 liters of hydrogen. But since we are not dealing with STP conditions, then we leave it in moles and we shall see later what to do. Because there, if it was STP, we will get your answer directly. So what shall we do? What we do in this case, we leave it in terms of moles. So if that charge liberates 1 mole of hydrogen, how about this charge? 322.56 coulombs. That charge will liberate 322.56 times 1 over 2 times 96500. And that gives us which amount of charge, which amount of hydrogen. These are moles, of course, because we are getting moles. The moles that we'll get here will be 0.000, it is 0.001, and then 671. Those are moles of hydrogen. I want you to see how I'm doing this question. That's some tricky bit of it. Then you go to the anode. What's happening at the anode? At the anode, we have 4 hydroxide ions giving us oxygen, 2 water, 4 electrons. Okay, so that implies that 4 moles of electrons liberate, liberate what? Actually, to use the correct word here, since electrons are on the product side, we shall say 4 moles of electrons are released with the 1 mole. We are looking at the gas, 1 mole of oxygen. So that means that 4 times 96500 columns are released with 1 mole of oxygen. How about the same charge here? Because the same charge that passes through the cathode is the same charge that passes through the anode. So that charge is released with 322.56 times 1 over 4 times 96500. And that gives us how many moles of oxygen? It will give us 0.000836 moles of oxygen. The moment you reach there, then you're almost finally finishing the calculation. So what do you have at the end? You get the total moles of gas liberated. Total moles of gas liberated will be moles of hydrogen plus moles of oxygen. So that will be the moles of hydrogen, which are 0.001671, plus the moles of these are moles of hydrogen. Moles of oxygen 0.000836. When you do the adding very well, you will get 0.002507. Those are the total moles of gas liberated. Now remember, you were given the pressure as 100 kilopascals. Convert it to pascals, that is 100 times 1,000. Kilo means 1,000. There it remains in pascals. We are also given the temperature as 15 degrees Celsius. Convert it to Kelvin. When you add 273 there, it will be converted to Kelvin. So they're asking us volume. We know it that from PV is nRT, it implies that our V, which is the total volume of gas, is nRT over P. Yes, over P, by dividing through by P here. N is 0.002507. Let me shift it down to simplify my work. So our V will now equal to N is total number of moles. R is 8.31. T is 15 plus 273. What is your pressure? 1,000 times 100 times 1,000. And I told you the moment you do these conversions, your volume is always in meters cubed. If you want it in centimeters cubed, you will convert it. But the moment you use number of moles, R as this, temperature in Kelvin, pressure in pascals or Newton per meter squared, your volume should be meters cubed. And the answer you'll get here will be approximately 6, 10 power negative 5 meters cubed. Let me hope this calculation has not been a burden to you guys. Is it fine?
Yes, teacher.
Okay. We still have some good examples, and I have a reason as to why I'm doing all of them. I have a reason as to why I'm doing all of them. You know, electrolysis has a tricky kinds of calculations that usually people want you to go through. Our next question is question 7. Question 7 says that calculate the volume of oxygen gas liberated at anode if at STP, if copper 2 sulfate solution was electrolyzed for 10 minutes using a current of 1500 milliamperes. That's the question. So how do you approach this question, dear friends? You have Q equaling to IT. You have the I, you have the T, get the charge. What's your I? 1500 milliamperes means multiply by 10 power negative 3 to convert it to amperes. What's your time? 10 minutes. Each minute is 60 seconds. When you do that, your work is simplified. Actually, you get 900 coulombs as the charge. What's the equation at the anode where oxygen is liberated? What are we electrolyzing? Copper 2 sulfate solution. Take some theory here. Copper 2 ions, hydrogen ions are in copper 2 sulfate solution. Hydroxide ions from water, then sulfate ions from copper 2 sulfate. It is this one that will be discharged at the anode because it's low in electrochemical series. So that means you know this equation. Oxygen. By this time, you should be knowing how to write it well balanced. So that's the equation for reaction at the anode. So what do we have here now? 4 moles of electrons are released together with 1 mole of oxygen. How about, actually this is 4 Faradays, 4 times 9, 6500 coulombs of electrons are released with, since we are dealing with STP, my pen is becoming hypersensitive. So are released with 1 times, since we are dealing with STP, convert 1 mole to volume at STP, which is 22.4 liters. That's it now, mole concept into play. Now, how about the 900 coulombs? What's really happening? There's a lot of sensitivity here. So how about the 900 coulombs? Actually, this should be charge now, of charge are released with, do the mathematics, that's 900 times 22.4 out of 4 times 96500 liters. And from that, you're going to get your answer. You're going to get your answer as which answer do you get? I'm pretty sure your answer will be 0.0522 liters. I'm pretty sure your answer is going to be 0.0522 liters. I think that's also fine, and it's a bit shorter and an easy route to the answer. Whenever whenever you see me doing something on a line like this, I'm trying to show you how you always use the minimum space you have. If you decide to go on dropping everything down, you may not use the space well if you're in an exam. So basically, that's the best way to approach or to present your work, especially in paper 1. It simplifies your work and helps you maximize the space that you're always given, and stop complaining of having limited space. Our next question is question 8. Is question 8. Question 8 says a current of 32.2 amperes was passed through molten lead to bromide for 5 hours. And the bromine liberated reacted with 94 grams of hydroxybenzene. Calculate the number of moles of Roman 1 bromine liberated, Roman 2 number of moles of hydroxybenzene that reacted. When somebody talks of hydroxybenzene, that person is confusing you. Hydroxybenzene is simply phenol. State what is observed. These are questions that are still silent in the bank. We have them sleeping there, waiting for some time to come out. State what is observed and write equation for the reaction that took place between bromine and hydroxybenzene in A above. That's our simple question. What do we have? We have our current as 32.2 amperes. That's the current we have. So we have I. We have the time. That means we can get a charge. And let's begin from there to do Roman 1. Okay. In Roman 1, we have our We have our charge equaling to IT. The current given to us is 32.2 amperes. The time is 5 hours. 5 hours should be in seconds. Don't be a mistake to leave it in hours. When you multiply something like that, you will get 5, 7, 9, 6, 0, 0 coulombs. That's the time, the charge you get. Now they're asking us moles of bromine liberated. How do you get moles of bromine liberated? The bromine is liberated where? That's where the bromide ions move to. And that should be the anode. So we write equation at the anode. The equation at the anode is simply bromide ions in liquid form, giving us bromine in liquid form, put a 2 here to balance, and then 2 electrons here. Why am I using liquid state? This is molten lead 2 bromide. It's not a solution. Molten lead 2 bromide is insoluble in water, so we cannot electrolyze it when it is dissolved in water as a solution. It is simply molten, heated to melt to form a liquid. Are we together, members?
Yes, teacher.
So molten lead 2 bromide is a liquid. That's what we have at the anode. So we have it that 2 moles of electrons are released with 1 mole of bromine. That's what we do have. So if we have that, that implies that 2 Faraday are released with 1 mole of bromine. How about this charge? 579600 coulombs. Do the calculation. 579600 times 1 over 2 times 96500. If you do the calculation very well, you will happily get a good number of moles of bromine, and that will be 3 moles of bromine. Whenever you see such a question, your answer must be 3 moles of bromine, whichever values you're given, as long as the reaction is between bromine and hydroxybenzene, because the bromine liberated is now reacted with hydroxybenzene. Now somebody is asking you to get the number of moles of hydroxybenzene that reacted. Number of moles of hydroxybenzene that reacted. It is this mass of hydroxybenzene that you are going to convert to moles. Get the number of moles of hydroxybenzene that reacted. So are you following?
Yes, teacher, I'm following.
Yes. Now you get the molar mass of hydroxybenzene. Molar mass of hydroxybenzene. Hydroxybenzene is this compound phenol. Okay. It is simply phenol. And phenol is the same as C6H5OH. The ring alone is this. So you get molar mass of C6H5OH. 6 times 12, that is 72. Plus 5 for hydrogen, plus 16 for this oxygen, plus 1 for this hydrogen. The total there is going to be 94 grams. So what are the moles of hydroxybenzene that reacted? Because that's what the question wants. It is the mass given in the equation over the molar mass, which are both similar. So maybe the difference is that we may call this 94.0 because the equation gave us a mass of 94.0, but that's the same thing. So this gives us 1 mole. And that implies that for every 1 mole of hydroxybenzene, it reacts with 3 moles of bromine. What is observed and write equation? First of all, write the equation before you make the observation, because you don't know. What is the equation for the reaction? This same equation was set in last year's paper. So the equation here is this. This is hydroxybenzene. Hydroxybenzene is a solid. Phenol is a solid. Phenol is a solid. That is its physical state. It's a solid substance. It reacts with bromine, a liquid. It ends up giving us this substance here. The OH remains here. At this corner, there will be a bromine atom. That corner, you have a bromine atom. That corner, you have a bromine atom. That compound there is called 2,4,6-tribromophenol. That's its name. 2,4,6-tribromophenol. Then this is plus HBr. HBr can be liquid or it can also be aqueous. So how do you balance this? You put a 3 here and a 3 here. The equation simply gets balanced. What's the observation? This solid compound formed here is usually a white precipitate. So this strictly corresponds with what the equation. You see that this is 1 mole of hydroxybenzene reacted with 3 moles of bromine, as we have calculated here. So that was the aim of that kind of question. So the aim was that electrolyze ready to bromide, get the bromine. The bromine you get, react it with phenol and get that white precipitate. Are we together?
Yes, teacher.
All right. Another question. I should do all of these questions. My mind tells me to do all of them so that you follow them. We have 20 centimeters cubed of 0.05 molar aqueous phenylamine. Was mixed with 50 centimeters cubed of 1 molar sodium hydroxide. Sorry, sodium bromide. This question is a bit similar to the previous one I've just done. When the two were mixed, what really happened? There was electrolysis. and electrolyzed at a current of 0.2 amperes, the first bromine color, because bromine is liberated, the first bromine color was observed after 48.25 minutes. And then electrolysis was stopped. You could ask yourself, why was the electrolysis stopped? After the first bromine color was seen. The question is asking us to calculate the moles of bromine that reacted with 1 mole of phenylamine. Roman 2, hence write equation of the reaction between bromine and phenylamine. Name the major product. Name the major product. This is the question we have now. And what are we going to do? We have this solution of phenylamine, aqueous phenylamine. That means from that we can get the moles of phenylamine. Can get the moles of phenylamine. It was reacted with these moles of sodium bromide mixed with this. Actually, it didn't react, but it was mixed with these moles of sodium bromide and electrolyzed at that current for that time. Calculate the moles of bromine that reacted with 1 mole of phenylamine. So I want you to know the theory here. The theory is that when you electrolyze, phenylamine is can't be electrolyzed. It's a weak electrolyte. But you have sodium bromide, a strong electrolyte. Sodium bromide on electrolysis will give us bromine. Where is the bromine liberated? At the anode. We shall have bromine liquid being liberated there. Here we may use a state of aqueous for the ions because sodium bromide is soluble in water. So we can have bromide ions aqueous. It's fine. Now the bromine liberated there is liberated by this at this time and using that current. Meaning you can get the quantity of charge that liberates that bromine and use that charge to get the number of moles of bromine that was liberated there according to this Roman 1. Okay, these moles are moles of sodium bromide electrolyzed, but not actually, this one is in excess. Not all of it was electrolyzed. So sodium bromide was such an excess that enough bromine must be liberated to react with all the phenylamine. And that first bromine color they are talking about only appears if just enough bromine has been formed to react with all the phenylamine. Hope you're getting me. So we don't use this anywhere in the calculation. We begin with the time and the current to get the charge. So that's Roman 1, Q is equal to IT, is equal to 0.2 times 48.25 times 60. Minutes times the seconds will give us the time in seconds. When you do that, you get 579 coulombs. Then write equation at the equation for liberation of bromine, that is at the anode. What happens there? The bromide ions give us bromine liquid, 2 electrons. So if that is what happens, relate this charge which you have calculated with what you have here. So have 2 Faraday, 2 moles of electrons liberated for 1 mole of bromine. That is 2 times 96500 coulombs of charge for 1 mole of bromine. How about the 5? This charge here, 579. 579 coulombs. I'm telling you the answer here should always be 3. When you meet such a question in electrolysis, the answer should be 3. 579 times 1 over 965, or a factor of 3. If it's not a 3, then it's a factor of 3, such that later when we deal with the molar ratio, then we shall get it as 3. For example, this one will give you 0.003 moles of bromine. That's what you have. Then in Roman 2, they're asking us, actually what I want you to know is that the sodium bromide was in excess so that we get enough of the bromine. But all the phenylamine must have reacted. All the phenylamine must have reacted with the bromine liberated from sodium bromide. So these are the moles. The moles of phenylamine, for them, we'll get them from here. Okay? Moles of phenylamine that reacted, we get them from here. So we shall say moles of phenylamine, C6H5NH2, that reacted will be how many of them? 20 times 0.05 over 1000. My dear students, this gives us 0.001. The question is asking us to get what? It is asking us to get moles of bromine that reacted with 1 mole of phenylamine. We are still on Roman 1. 1 mole of phenylamine. So according to this, 0.001 moles of phenylamine react with 0.003 moles of bromine. How about 1 mole they are talking about? 1 mole of phenylamine reacts with, you see how the 3 now comes in? 1 times 0.003 out of 0.001. That will give us That will give us 53 moles of bromine. Then they're asking us to write the equation. The equation is similar to that of phenol. The equation is phenylamine for it is in solution. It's reacting with 3 moles of bromine. Bromine is aqueous because the sodium bromide is soluble in water. This gives us the same compound as we saw for phenol. What differs is its name now. There's a bromine atom here, a bromine atom here, and a bromine atom here. This is a solid, it's a precipitate. Actually, it is also a white precipitate, just like we saw for phenol. And then 3 hydrogen bromide. What's the name of this compound? They asked us the name of the major product. This compound is given a name of, this is position 1, this is position 2, 3, 4. So it is 2,4,6-tribromo-phenylamine or tribromoaminobenzene to make it IUPAC. 2,4,6-tribromoaminobenzene. Let's have our final calculation. Anyway, the final calculation, you'll go through it by yourselves. Try to go through it by yourselves. Then in our book, Demystifying Physical Chemistry, we have about 14 questions about those calculations. Try to go through those 14 questions about those calculations. Those of you who don't have that book, Demystifying Physical Chemistry, you contact me and get it. It can be delivered to you wherever you are. Muhammad, you have a question?
So on number 13, the exercise. What is the effect of when the temperature increases? For example, it was at 20 and the temperature increased to 30 degrees.
The speed of migration of the ions increases. When you look at question 13, it says that during electrolysis of 1 molar copper 2 sulfate solution at 20 degrees Celsius, a current of 0.1 amperes was passed for 1 hour through the electrolyte. The mass of copper cathode increased by 0.001. That means some copper was deposited at the cathode. And that amount of copper, 0.118 grams, the mass of copper that was deposited at the cathode. State how the change in mass would be affected if the experiment was repeated at a current of 0.2 amperes. So the mass of, if the current is increased, the mass of copper, would increase. The mass of copper that is deposited at the cathode would increase. Then if it is carried out at 30 degrees Celsius, that's an increase in the temperature. So when this was at 20, then the solution was electrolyzed at 30. At 30, that means you have increased the temperature, then you have increased the speed of migration of the ions in solution. That means the more copper will get deposited, so the mass of copper will still increase. Are we together?
Yes, teacher.
So Our next concept, excuse me, our next concept is applications of electrolysis.